Hello viewers, today we will see the higher order derivatives of analytic functions exist on the domain of analyticity of a analytic function. So, this will imply that the differentiation of an analytic function we will see that this will imply that that is also an analytic function. So, I will start with a reminder of the third version of Cauchy's theorem, which tells you that if you have a positively oriented simple closed curve and then f is analytic on and inside this simple closed curve, and if you have yet another simple closed curve contained in the inside of the first curve, then integrating f on the first curve is the same as integrating f on the second curve. Okay. So, that was the deformation theorem or Cauchy's theorem version 3, and we will put that to use today. So, today we are going to see higher order derivatives of an analytic function. Okay. So, here is the setup. Let f be a holomorphic function. Okay. So, let f be a holomorphic or analytic. So, I explained that holomorphic is another word for analytic, holomorphic. Okay, inside and on a positively oriented simple closed curve gamma. Okay. So, then the conclusion is that then f of z is, well, this we know from Cauchy's integral formula. Okay. So, that f of z is 1 by 2 pi I integral over gamma f of w by w minus z dw, okay, for z belongs to I of gamma, the interior of the simple closed curve gamma. Okay. So, now intuition is that we will be able to differentiate under the integral. Okay. So, hopefully, if we are able to differentiate under the integral sign, then we hope to say that f prime of z is 1 by 2 pi I times the integral over gamma of the differentiation with respect to w. We hope to write this as w minus z squared, minus and a minus cancel dw. Okay. So, this we hope. Okay. So, but we should justify the differentiation under the integral sign in order for us to be able to do this, and that is the content of what follows. So, what I will do here is I will follow the textbook Priestley, and in here first I will try to justify the formula for or justify this Cauchy's integral formula for f prime, okay, which we wrote as hope here. Okay. And then I will justify or produce a formula, Cauchy's integral formula for f double prime of z, okay, and then show that higher order derivatives of f exist, or in other words all derivatives of all orders of f exist. And then I will give a proof based on induction to produce the formula for Cauchy's integral formula for all higher order derivatives. Okay. So, so that is the program. Okay. So, here I start with the following. I will start with the first derivative. Okay. So, Cauchy's integral formula, okay, for first derivative. So, this is about the justification of differentiation under the integral. Okay. So, let here is the setup once again, let f be analytic on and inside a positively oriented simple closed curve gamma, okay, and let A belongs to the inside of the simple closed curve gamma, okay. Then f prime of A is 1 by 2 pi I integration over gamma of f of w by w minus A squared dw. Okay, so that is your Cauchy's integral formula for the first derivative. Okay, so we will prove this here, okay, and notice that I will I just said simple closed curve gamma where A belongs to the inside of the gamma. Okay. So, the idea of the proof is that I will take this simple closed curve gamma, okay, positively oriented, and here is A. Okay. I will replace gamma by a circle of radius r or 2r around A, okay, where 2r such that this disk of radius 2r, closed disk of radius 2r around A is completely contained inside this curve gamma. Okay. So, now notice that the integration on the boundary of this disk is the same as the integration on this curve gamma of the integrand. Okay. That is because we will use the Cauchy's theorem version 3. Okay. So, that is the idea, and then we will be able to do something with this circle of radius 2r. Okay. So, here is the proof. Okay. So, we can replace gamma with a circle gamma A to r. So, recall gamma A to r is a circle centered at A and of radius 2r, okay, and it is oriented in the positive sense, okay, and we get, so we can replace that with that. We will decide what r is shortly, okay. So, such that at least we need the following of r such that this circle gamma A to r, okay, and its interior, okay, and the inside of gamma A to r are contained in the inside of gamma. Okay, that we can do by Cauchy's theorem version 3. Okay, can do so by Cauchy's theorem version 3. Okay. Okay. Now, we will calculate this quotient f of A plus h minus f of A by h, which in the limit will give you the differentiation of f. Okay. So, using the Cauchy's integral formula for f, which we have already proved, this is 2 pi I times 1 by 2 pi I times, well, there is this h in the denominator, okay, and then integral over this gamma A to r. I am going to apply Cauchy's integral formula for f of A plus h, that will give me f of w by w minus A minus h, and then I am going to apply Cauchy's integral formula for f of A, that will give me f of w by w minus A, okay, all this times dw. Okay. So, I am using the Cauchy's integral formula twice, and upon simplification this gives 1 by 2 pi I, okay, and this h in the denominator cancels with the h I am going to obtain when I add these two expressions or subtract, whichever way you consider it, okay, and then w minus a minus h times w minus a. Okay, once you make these two expressions into one, you get a h in the numerator that cancels with the h outside, and then you get this dw. Okay. So, now the idea is hopefully this, when this h is small, okay, when you take the limit as h goes to 0, the idea is the integrand will become w minus a whole square. Okay. So, we will justify that. Okay. So, here is what we have. So, f of a plus h minus f of a by h minus 1 by 2 pi I, okay, integral over gamma a to r f of w by w minus a squared dw. Okay. So, we obtained this expression 1 for the quotient f of a plus h minus f of a by h. Okay. So, what we are going to do is we are going to estimate the difference between this quotient and this integral here. Okay. This is different, notice, from the expression we got from 1. Okay. So, that difference is equal to 1 by 2 pi I times the integration over gamma a to r of I am using 1 now. Okay. Then I get f of w times 1 by w minus a minus h times w minus a, that is from your 1, okay, and then minus 1 by w minus a squared, that is from this difference here, that is the second expression here. So, I am subtracting the integrands and then I get this, okay, that is your difference here, okay, this difference here. Okay. So, then that is 1 by 2 pi I. After clearing the fraction, I get integral gamma 0 to r, or a to r rather, a to r f of w times h divided by w minus a minus h times w minus a squared dw. Okay. So, I will transfer the h to the front, okay. It is free of the integrand. So, I will just, or integration rather. So, I will move that to the front. Okay. So, now the claim is, so here is the claim. Now, the claim is that as h approaches 0, okay, this integrand, okay, this not just the integrand, this expression, okay, this expression here tends to 0, okay, approaches 0. So, that is the idea, and in order to prove that that approaches 0, we will use the estimation theorem that we talked about few sessions ago, okay, and that is a useful tool when you want to estimate something, and after showing that that tends to 0, we would have shown that this difference in the limit here, okay, tends to 0 as h tends to 0, which means the differentiation, this quotient here is your differentiation, right, of f when h tends to 0. Okay. So, we would have shown that f prime is equal to this integration or this integral here as h tends to 0. Okay. So, well, this integration is free of h. So, the differentiation of f would be equal to this, and which is the Cauchy's integral formula for f prime. Okay. So, we will do that, we will show that this approaches 0 as h approaches 0. Okay. So, choose h. Okay. So, the idea is as follows, you choose h such that the modulus of h is strictly less than r. Okay. So, the modulus of w minus a minus h is going to be greater than or equal to modulus of w minus a minus modulus of h, that is by the triangle inequality. Okay, the triangle inequality, and then that is strictly greater than r, because well, okay, for W belongs to gamma A to R star, the trace of gamma A to R. Okay. So, what is happening here is you have A, okay, and then you have a circle of radius 2r. Okay. So, that is the circle of radius 2r. I will show the radius 2r. Okay. And as your W varies on this circle, W can be any point on this circle. Okay. So, you choose h so that the modulus of h is less than r. Okay. So, that well, so a plus h is a vector which is somewhere inside. So, this is a circle of radius r. Okay. The dotted circle is a circle of radius r. Your a plus h is some point within this disk. Okay. Anywhere it is, you see that the shortest distance from a plus h to this circle of radius 2 r, okay, is at least r, is at least r. Okay. If you suppose that is your a plus h, then it is at least this distance, that distance to that circle of radius 2 r is at least r. Okay. So, that is the idea. So, this is strictly greater than r. Okay. And we will use this to say, okay, okay, we will actually use this to estimate the denominator. Okay. Now, we will also do something about the numerator. Okay. Since f is continuous, I am talking about the denominator and numerator in this expression, of course. Okay. So, in the numerator, since f is continuous on the trace of gamma a to r star, or trace of gamma a to r, okay, which is a compact set, it is a circle. So, it has to be a compact set, okay, which is a compact set. We know that a continuous function on a compact set assumes a maximum value. Okay. So, actually the modulus of f assumes a maximum value. Okay. So, there is an m such that the modulus of f of w is less than or equal to m. Okay. So, okay. So, f is continuous and the modulus is a continuous function. So, the modulus of f is a continuous function on this compact set. So, it assumes a maximum value, okay. And then the modulus of f of w is bounded. Okay. So, for w with modulus of w minus a equals to r, that means for w on that circle, okay, of radius 2 r, what we have is the modulus of f of a plus h minus f of a by h minus 1 by 2 pi I integral over gamma a to r f of w divided by w minus a square dw. Okay. The modulus of this quantity, which is here, okay, which is underlined here, okay, is equal to the modulus of this quantity of the expression which we are handling. Okay. So, is less than or equal to, okay, well, firstly let me write that expression, is equal to the modulus of 1 by 2 pi I or h by 2 pi I times integral over gamma a to r of f of w by w minus a minus h times w minus a squared dw. Okay. So, this is less than or equal to well, modulus of h by 2 pi integral over gamma a to r, the modulus of f of w divided by the modulus of w minus a minus h times the modulus of w minus a squared times the modulus of dw. Okay, that is by the estimation theorem. Okay, and this is less than or equal to the modulus of h by 2 pi we know that the modulus of f of w on gamma a to r is less than or equal to m, okay, because f is bounded on a compact set. Okay. And then in the denominator we know that the modulus of w minus a minus h, we showed that that is at least r. So, it is here, that is at least r. Okay. So, 1 by that is at most r, okay, and likewise w minus a in modulus is equal to r. Okay. So, this is equal to 2 r rather. Okay. So, this is 2 r squared, okay, and then this quantity is at least r. So, 1 by that is at most 1 by r. Okay. So, we get r times 4 r squared 4 r cube here, okay, times this 2 pi times the radius, radius is 2 r. Okay, that is the length of the curve. Okay. So, all in all this quantity, okay, this quantity on the right hand side tends to 0 as h approaches 0. Okay. Clearly, the modulus of h in the denominator, the others are all constants. Okay. So, the modulus of h in the numerator causes this quantity to go to 0. And notice that the quantity on the left hand side, okay, then is equal to 0 in the limit as h goes to 0. Okay. So, the limit as h goes to 0 of f of a plus h minus f of a by h minus 1 by 2 pi I integral gamma a to r f of w by w minus a squared dw, this is equal to 0, okay, according to this estimate. Okay. Actually, the modulus of this is equal to 0, but of course, the only complex number with modulus 0 is 0. So, this has to be the case. Okay. So, since this quantity is free of h, we only take the limit for this quantity, which is f prime of a, okay, and that we declare is 1 by 2 pi I integral over gamma a to r of f of w by w minus a squared dw. Okay. And by the deformation theorem, like we remarked earlier, that is equal to 1 by 2 pi I the integration over gamma of f of w by w minus a squared dw. Okay. And that proves the Cauchy's integral formula for the first derivative. Okay. So, this is f prime of a. Now, the situation was your f is analytic on and inside the simple closed curve gamma, okay, and a is in an arbitrary point on the inside of gamma, okay, and this formula holds for a. Okay. So, you can think of a varying on the inside of gamma. Okay. So, so a can be any point. So, you have a variable point. So, we usually write this formula as f prime of z, just to remind you that it is a variable point inside the closed curve gamma, simple closed curve gamma, 2 pi I integral gamma f of w by w minus z squared dw for z belongs to the inside of the simple closed curve gamma. Okay. And notice that gamma should be oriented in the positive sense, okay, and of course, the simple closed curve. Okay. So, that is your Cauchy's formula for the first derivative, and using this what one can show is that one can extend this formula for the second derivative as well. So, we will extend this, and not only that, we will show the following theorem. Okay. So, suppose that f is holomorphic, that is analytic, okay, in an open set G. Okay. Then the first statement is that f prime is also analytic. in G. Okay. And from the first statement we can conclude that f has derivatives of all orders in G, right. If we show that f prime is analytic in G, okay, then we can apply the first statement to f prime which is analytic in G and show that f double prime also exists, okay, and we can continue this and say that the derivatives of all orders of f exist. Okay. So, the proof of second statement is direct using the first statement. Okay. So, we have to prove the first statement here. Okay. So, let A belongs to G, since G is open, okay, there is capital R positive such that the ball of radius R, okay, around A is contained in G. That is the definition of open set. Okay. So, choose little r such that 2 r is strictly less than capital R. Okay. So, that a ball of radius 2 r is contained in G. Okay. Not only that, the closure of the ball of radius 2 r is also contained in G, and the boundary of this, which we typically denote by gamma A to R, okay, is contained in G. So, this is what we will need. Okay. So, this implies that gamma A to R, so gamma A to R star, which is circle of radius 2 r centered at A, okay, however parameterized however, but oriented in the counterclockwise direction, okay, is contained in G, okay, and the inside of this is also contained in G, Okay. This is what we want. Okay. So, now we will look at this quotient f prime of A plus H minus f prime of A divided by H. Okay. Like we did for the previous proof, we will consider this quotient, okay, and we will notice that this is 1 by 2 pi I times H. Okay. This H in the denominator I am carrying it forward, and I will use the Cauchy's integral formula for the first derivative, which was proved in the previous theorem, on f prime of A plus H and on f prime of A. Okay. So, that will give me integration over gamma A to R of f of w by w minus A minus H squared minus f of w by w minus A squared dw by previous theorem. Notice that we restated it here shortly. Okay. Z can be any point in the interior of the simple closed curve gamma. Here Z, okay, instead of Z I have w minus A minus H once, and then I have, or rather A plus H once, I apologize, A plus H once, and then I have A for the second instance of this formula. So, then let us see that this is 1 by 2 pi I H. Upon simplification, this gives us integration over gamma A to R, and then f of w divided by w minus A minus H squared times w minus A squared. Okay. I took the common denominator, and then I have w minus A squared minus w minus A minus H squared dw. There is some cancellation when you expand these squares. Okay. So, you get gamma A to R f of w divided by w minus A minus H squared times w minus A squared. So, w square cancels with w square here, A squared cancels with A squared. So, we are left with well, 2 A w also cancels. Okay. So, we are left with minus H squared from the second part, okay, and then we are also left with well, minus h squared, and then we have minus 2 w h plus 2 a h d w. So, from here actually this should be 2 plus 2 w h minus 2 a h, right. So, including that minus sign. Okay. So, what I will do is I can filter out or factor out a h, so that I can cancel with the h which is in the front here. Okay. So, I get 1 by 2 pi I times the integral over gamma a to r of f of w by w minus a minus h squared w minus a squared times 2 w minus 2 a minus h. So, allow me to write this as minus 2 h plus h. Okay. So, that what I can do is I can separate this integral into two things. Okay. So, this is gamma a to r times f of w divided by w minus a minus h squared times w minus a squared times 2 times w minus a minus h, okay, and then plus well dw. So, I will separate the integrals. Okay. So, this plus integral over gamma a to r f of w divided by so times h divided by w minus a minus h squared times w minus a squared dw. So, now we are estimating this quantity. Let us estimate f prime of a plus h minus f prime of a divided by h. Okay. So, this expression 1 is this expression here, okay, and then let us subtract 2 by 2 pi I. So, 2 by 2 pi I integral over gamma a to r of f of w divided by w minus a cubed dw. Okay. So, this is the desired expression. We wish to show that in the limit this expression is equal to this expression positive or with a plus sign rather. So, this is what we wish to show. So, let us estimate this difference. So, the modulus of this difference is equal to the modulus of, for the first expression I will use this expression 1, okay, and say that it is 1 by 2 pi I times the integral over gamma a to r of f of w times 2 by what I have here is 2 by w minus a minus h times w minus a squared plus h divided by w minus a minus h squared times w minus a squared times dw, right. So, actually what I have done is I have cancelled the w minus a minus h here with one factor here, okay, and hence I have 2 by w minus a minus h times w minus a squared and then for the second integral here I have h divided by all that, h divided by all that. Okay. So, I have this expression and then you subtract 2 by w minus a cube and then times it by dw. So, all this is the integrand. So, I am splitting it into two lines for lack of space, but that is your expression. Okay. So, this is in turn equal to 1 by 2 pi I in the modulus, okay, within the modulus integration over gamma a to r of f of w times. So, let me combine the first, okay, and the third expressions here, okay. So, that I get 2 times. So, I get 2 times w minus a minus 2 times w minus a minus h when I take the common denominator w minus a minus h times w minus a cube. Okay. And then I will leave the second expression alone. So, that will be h divided by w minus a minus h squared times w minus a squared dw. Okay. So, so that what I get, so all this within modulus, this is equal to the modulus of 1 by 2 pi I integral over gamma a to r f of w, okay, times, well, after cancellation what I have in the numerator is 2 h, right, divided by w minus a minus h times w minus a cube plus h divided by w minus a minus h squared times w minus a squared dw within modulus. Okay. So, this is in turn equal to the modulus of 1 by 2 pi I integral over gamma a to r f of w. So, I am carrying out the simplification in 2 steps. Okay. So, that was the first simplification and this is the second simplification. I am going to write this as 2 times, well, there is a h common all throughout. So, I will push the h out of the integration into the numerator here, okay, and then 2 times w minus a minus h plus 1 times w minus a when I take the common denominator w minus a minus h squared times w minus a cube dw. Okay. So, after all that ordeal, we can use the estimation theorem now, okay, and say that on gamma a to r star f is continuous, okay, f is a continuous function, okay, and hence bounded in modulus like the proof of the previous theorem, okay, and hence bounded in modulus. Okay. Let f of z, okay, the modulus of rather w, I am using w here, f of w in modulus be less than or equal to m for as w belonging to gamma a to r star. Okay. So, continuous function on a compact set is bounded. So, that I am using like in the proof of previous theorem, if modulus of h is strictly less than r, if we choose h such that modulus of h is strictly less than r, then modulus of w minus a minus h is greater than or equal to modulus of w minus a minus modulus of h, which is strictly greater than r whenever w is on this trace of gamma a to r. Okay. So, that is very similar to the proof of previous theorem. Okay. And then what we can do is we can use all this to estimate what is within this modulus. Okay. So, let me call this 2. Okay. So, 2, the expression 2, that is the expression within the modulus is less than or equal to modulus of h divided by 2 pi. Okay. So, that is what is in the front, okay. And then the modulus of f of w is less than or equal to m. So, I have a m here, okay. And then the modulus of 2 times w minus a minus h plus w minus a. Okay. So, that is definitely less than or equal to 2 times r, okay, 2 times r plus 2 times r. Okay. So, this in modulus is less than or equal to 2 r definitely, okay, and then this in modulus is less than or equal to 2 r. Okay. So, I have 2 times r plus 2 r for the numerator, okay, and for the denominator I will use all this here. Okay. So, what I have is r w minus a minus h squared in the denominator, okay, is actually less than or equal to in modulus is less than or equal to r squared here, and then w minus a squared, well, w is on the trace of gamma a to r. So, that is 2 r and then times the length of the curve gamma a to r is 2 pi times 2 r. So, all in all this expression what does it come to? It comes to 4 plus 2 6 r. Okay. So, this is modulus of h m by 2 pi's cancel. Okay. So, this is 6 r times 2 r divided by 8 r power 5. So, that is what it comes to. So, the summary is, well, this goes to 0 as h goes to 0. Okay. The modulus of h in the numerator, whatever the other expressions are, they are all constants. Okay. So, that goes to 0, that takes the expression to 0 as h goes to 0. Okay. So, we conclude that f prime of a plus h minus f prime of a divided by h in the limit as h goes to 0, okay, is equal to 2 by 2 pi I integration over gamma a to r f of w by w minus a cube, okay, which in turn is equal to 2 by 2 pi I integral over gamma. Recall by deformation theorem, these two integrals are equal, or Cauchy's theorem version 3, these two integrals are equal. Gamma was a simple closed curve such that f is analytic on and inside this simple closed curve. So, we have proved this theorem. Okay. So, notice that f double prime of now z. So, we can treat a as a variable now, solely because a was an arbitrary point in the statement of the theorem. A was an arbitrary point. So, f double prime of z 2 by 2 pi I or 2 factorial by 2 pi I integration over gamma f of w by w minus a cube, okay, or z d w, okay, for z belongs to any of or the interior of gamma. Okay. So, that is the proof of part 1. Okay, part 1. Okay. Now, part 2 follows easily using part 1. F is analytic. What we showed is that if f is analytic in G, okay, then f prime is analytic in G. Okay. So, this is the proof of part 2. Okay. We showed by part 1, we showed that if f is analytic in G, then f prime is analytic in G. Okay. So, replace f by f prime in the previous statement. Okay. So, so f prime is analytic in G implies that f double prime is analytic in G. Okay. So, so on and so forth. So, replace f by f prime, and so f prime is f double prime is analytic in G, etc. So, you get that so derivatives of all orders of f exist. Okay. And that is the proof of part 2 of this theorem. Okay. So, that is the end of the proof of this theorem. So, we have proved the Cauchy's integral formula for the second derivative, okay, and we did that for first derivative, and we had a Cauchy's integral formula for the function itself. Okay. And what we are going to do next is prove the Cauchy's integral formula for the nth derivative. Okay. So, I will briefly give the formula for the nth derivative here. Okay. So, under appropriate conditions, the nth derivative of f at the point z, okay, is equal to n factorial by 2 pi I times integral over gamma, okay, integral over gamma f of w by w minus z power n plus 1 dw, okay, for z belongs to the interior of or the inside of the curve gamma. Okay. So, the appropriate conditions of course, are that gamma is a simple closed curve and that f is analytic on and inside this simple closed curve. Okay. So, given these conditions, we have a Cauchy's integral formula for the nth derivative. Okay. So, we can prove this using induction on n, which we will see next time. But for now we have the Cauchy's integral formula up to the second derivative at least. Okay. And when we see the general proof, we would have sort of overridden our proofs anyway, but the previous theorem at least gives us that the derivatives of all orders of f of an analytic function f exists in an open set when f itself is analytic in the open set. Okay. So, let us see an example, okay, of how to evaluate integrals using the Cauchy's integral formula. Okay. So, here is an example involving the second derivative. We can have examples involving higher derivatives as well once we prove the formula for higher derivatives. Okay. So, here is an example, evaluate the integration over gamma 0 to, recall what that is, it is a circle of radius 2 centered at the origin and then centered at 0, okay, and then it is oriented in the counterclockwise direction or in the positive sense, okay, and then z minus 1 cube e power z squared dz. Okay. So, evaluate this. So, rather that is z minus 1 power minus 3 times e power z squared dz. Okay. So, notice that z equals 1, okay, is a point which will appear in the denominator of the integrand, okay, or z equals 1 is a singularity of the integrand, okay, and this belongs to the inside of the curve gamma 0 2. Okay. So, what we will do is we will treat this as, okay, so this integral over gamma 0 to e power z squared divided by z minus 1 cube dz. Okay. So, we will view this as follows, we will take f of z equals e power z squared. Okay. So, that this looks like f of z divided by z minus 1 cube, the integration being over gamma 0 to, okay, d z, okay, dz, and so this is a simple closed curve, gamma 0 2 is a simple closed curve around the point 1, or it contains the inside of it contains point 1. So, here is 1, okay, and here is gamma 0 2, okay, this is 1 and this is 2, okay, circle of radius 2. So, by the Cauchy's integral formula, okay, so 1 by or 2 factorial by 2 pi I times this is equal to the second derivative of f at the point 1. Okay. So, this is the second derivative at the point 1. So, what we can do is we can say integration over gamma 0 2 of f of z divided by z minus 1 cube dz is equal to 2 pi I by 2, well, that is pi I times f double prime of 1. Okay. So, we can easily compute the second derivative of this function f of z equals e power z squared. Okay. So, this gives us 2 pi I by 2 times the second derivative, d squared by or the first derivative of e power of 2 z e power z squared. That is the first derivative of e power z squared, and then take its derivative again, okay, and all this evaluated at z equals 1. So, that is, well, that is equal to pi I times the differentiation of 2 z e power z squared is 2 e power z squared plus 2z times 2z 4z squared e power z squared, and all this evaluated at z equals 1. Okay. So, that gives us pi I times 2 e power 1 plus 4 times 1 times e power 1, which is 6 e. So, this gives us 6 e pi I, okay, and that is the value of this integral. Okay. So, okay. So, we can evaluate integrals of this type using Cauchy's integral formulae, okay, and particularly if the denominator, for example, here was z minus 1 power 4 or 5 or any higher integer, okay, we would have used the nth derivative formula, Cauchy's integral formula. Okay. So, we will see a proof of that next time, and then we will also see an easy consequence of the theorem we proved towards the end of this session. Okay. This theorem here. Sorry, let me go back. Okay. So, this theorem has an easy consequence, which is a partial converse of the Cauchy's theorem, okay, and that is called the Morera's theorem, and we will see a proof of that next time.